Okay, now that we know how to find z-scores given a normal distribution, we're going to today start to look at what we can do with those z-scores. But before we do that, I need you to go to Google Classroom and see what I posted in the stream. Either are two posts. One, they both say z-score table and examples. One says pictures, one says files. I have attached a picture of a z-scores table. A z-score table looks like this. That's the PDF file that I attached. The picture file is a different one, and it's 2 pages. Whichever one works for you is fine. Or you can certainly go to Google and just Google z-table and come up with whatever. All the tables are the same. They look a little different. Whatever you can. You must print this out or have it on your phone or something. The best is to print it out. If you can't print it out, you're going to have to deal with it on your computer, flip-flop back and forth to the pages, as you'll see that I'm going to do today. It's no big deal as long as you have a big screen. But get one of those printed out. You have to have those. The other file I attached the Word document in the file post, and I took a picture of it for the picture post. And these are going to be some of the examples that we're going to do later today. Okay, so what I want you to do now is to pause the video, please, and get that z-table chart and the examples out in front of you so you'll be able to work with these when we start talking about the examples. So please pause now and do that. So hopefully you have those in front of you. So what we're going to do first, we're going to take a step back and take a look at what we've been talking about. First of all, we're talking about normal distributions, and say we're comparing two normal distributions. Well, we can't compare. They always say you can only compare apples to apples. So let's say this is mangoes. I don't know how to spell mangoes. And this is bananas. You can't compare mangoes and bananas. So this would have a mean, I don't know what we're talking about, maybe the weight, I don't know, 13 ounces with a standard deviation of 2. Bananas maybe have a mean of 10 with a standard deviation of 1.3. So if I had a mango that weighed 15 ounces and a banana that weighed 12 ounces, which one is the higher weight compared to its distribution? Where does it fall in this distribution to be 15 ounces, and where does this banana fall in this distribution? Well, what we're going to do, and what z-scores do, is we're going to take each one of these distributions and we're going to standardize these distributions. And what we're going to come up with is called the standard normal curve. Every normal distribution can be standardized, and how you do that is every score just gets converted to a z-score. And in a standard normal curve, the mean will always equal 0, and the standard deviation will always equal 1. And that gives us our standard normal curve, and you've seen this picture before. These, of course, are negatives. So what we're going to do is we're going to standardize these scores and take a look at them to see which one is the more better rate. So how we're going to do that is we're going to find the z-score. So z is equal to x minus mu divided by sigma. So that's going to be 15 minus 13 divided by 2, which is 2 divided by 2, or it has a z-score of 1. Over here, we've got a z-score of x, our raw score 12, minus 10 divided by 1.3. So 12 minus 10 is going to be 2 divided by 1.3. Which is a z-score of 1.54. Remember, z-scores always get rounded to 2 decimal places. So both of these now, we're comparing mangoes and bananas, but once we standardize them and get a z-score, this is now an apple, this is now an apple, and we can compare them. So this banana is the bigger in its distribution as compared to this mango. It is smaller because it has a z-score of 1, and this one is at 1.54. Okay, that's one benefit of using a standard normal score or a z-score. Okay, now we're going to talk about something else. Okay, again, in our standard normal curve, every standard normal curve has a mean of 0 and a standard deviation of 1. Now, what happens is, and you would need calculus to figure this out, the area underneath the curve, so all of this area, come on, right, all of this area underneath this curve, so the area under the curve is equal to 1, which represents 100% of the population. So basically, and you all have heard of percentile rankings, and when you take your SATs or your PSATs, you score in the 85th percentile. That means somewhere up here, then there is going to be 85%, or 0.85 area under the curve. So you scored better than those. So your z-score is up here, and I don't have it figured out, so I can't give you a z-score. Trying to, oh boy. Okay, I'm going to pause here for a second. So basically, what we're going to do is we're going to use this standard normal curve to find probabilities and percentile ranks of certain distributions or certain items in distributions. And if you recall, there's 2 ways we're going to do this. We're going to do this with the fact that between +1 and -1 standard deviations, I told you there was 68.2% of the population. Let's just round that to 68%. Between -2 and +2 standard deviations, there's going to be 95.4% of the population. Well, we'll just call that 95%. And between -3 and +3, that was almost the entire population of 99.7%. We'll leave that at 99.7 because that's important to show that it is almost 100%. So we can find different probabilities using this. So now what we're going to do is we're going to go over to the example and look at number 1. So it says the lifetimes of 10,000 watch batteries are normally distributed. The mean lifetime of 500 days. So we've got a mu. Whoops, he's got him up the pen. We've got a mu of 500 and a standard deviation of 60. And it's normally distributed. Okay. Another way of writing this distribution is a capital N. Why is it boxing? What am I doing? You write a capital N. My apologies. Okay, let's try this again. Another way of writing this distribution is a capital N, and then in parentheses, the first number would be the mean, and the second, looks like an ordered pair, but it's not, would be the standard deviation. And that represents a normal distribution with a mean of 500 and a standard deviation of 60. It's just a way of condensing it. We want to sketch a normal curve that represents this distribution, label the mean and 3 standard deviations. All it's asking for is, let's just go ahead and draw a normal distribution. They all look like the same bell curve. label the mean. Well, that's easy, 500. And we want to label 3 standard deviations. So that's going to be 560. Second one is going to be another 60 added to that. So that's going to be 620. And the third one is going to be 680. In the negative direction, we're going to subtract 40 from 500. So that's going to be, we're going to subtract 60 from 500. So that's going to be 440. We're going to subtract another 60 from 440. That should give me 380. And we're going to subtract another 60 from 380. And we're down to 320. So that's what this distribution looks like. Now we're asking questions here. How many watch batteries will last for the following intervals? Well, we're going to look from 440 to 560. Well, 440 to 560 is right here. 440 to 560. So we're looking for the probability that the battery life is between these two intervals. We're looking for the area under the curve, because remember, the area under the curve is 1 or 100%. Well, this is between -1 and +1 standard deviations. So that's going to be 0.68 or 68%. Okay, the next one is between 380 days, which is right here at -2 standard deviations, and 620, which is at +2 standard deviations. And again, that's a pretty easy problem because we're at -2, +2, and that's just going to be our 0.95 or 95% of the population. And the next one is going to be 320. Well, that's -3. 680, that's +3. So that's our 0.997 or 99.7% of the population. That's easy enough. Now, let's take a look at one that you have to do a little more work with. Oops, got my eraser. And let's say we want to find how many watch batteries are going to be between, let's say, 380 days to 560 days. Right, 560 days is at +1 standard deviation. 380 is at -2. Okay, well, let's break this into 2 categories. We've got all of this area in here. We know that that area is 0.68%. And then we're going to have to find this area in here and add it to that. Well, how big is this area in here? Well, I know from here to here is 95% or 0.95. And I know that in the middle here, that's going to be our 0.68. So let's take 0.95 and subtract 0.68 from it, which is 0.27. But that 0.27 takes in this part and this part, and we only need half of that. So we're going to have to take 1/2 of that part, and 1/2 of 0.27 is 0.135. So basically, in this area right here, we've got 0.135. So that's what we have to add . So when I take these two and combine them, that gives me a total of 0.815, or we're looking at 81.5% of the batteries will have a lifetime between 380 hours and 560 hours. Okay, I hope that makes sense to you. Well, I was going to go ahead and do example 2, but I think this is already about 15 minutes long, and maybe that's just enough to digest for today. I guess it'd be Monday till we go over the second example, and that'll take us a few days to go through that and fully understand it. So hopefully you get this, watch it as many times as you need, ask me any questions you want, and I'll post up some problems on Google Classroom for you.